This is Physics Lab 4 by Alejandro Molina. The purpose of this lab was to analyze the motion of a spring. Our models include our energy time graph, two comparison position time graphs, then our fundamental principles were Newton's second law, position update formulas, Hooke's law, and energy principle. Our results was that due to air friction and deterioration of the spring's stiffness, the system loses energy, so energy is not conserved. So these are our functions, our equations. They have Newton's second law, Hooke's law, position update, and of course gravity. So here is our analysis of the system and surroundings. So let's watch this video. So as you see there, the spring and gravity are working on our system, which is the weight. As I said previously, the surroundings are the Earth and the spring, because the Earth is giving gravity force and spring is giving spring force. Our initial conditions were that the velocity of the weight was initially 0. Our gravity was 9.81 meters per second squared, and our force due to spring is negative k times s. So here is our code for our computational model. As you can see, there is our L naught, our spring constant. That was all determined from our original video that was posted on Canvas. Then all of our equations, energy equations, total energy is equal to kinetic times potential gravity energy and potential spring energy. Then our other equations like F spring, F net, and our position and velocity update formulas. Here we can see our calculation of S, our calculation of energies being updated, and our L being updated as well. So this is model 1. This is the energy graph. As you can see, delta kinetic energy is in blue. Our potential energy for gravity is red, it's constant. Our potential energy for the spring was, as you can see, that green line, and our potential energy, our change in energy for energy is that green line, and you can see it changes in some places, and that we assume is due to the other factors playing into our energy not being conserved. Then our model 2 for position time graph, you can see in the x direction we have our model and our experiment. They're pretty much the same, since similar to projectiles, the x direction doesn't really change that much except for air friction. Meanwhile, here in our position time graph for y, we can see a little bit more difference, but that is because of the deterioration of the spring stiffness, and it just being a imperfect spring system. So what does it mean? So was the energy principle satisfied? Of course, our system has to obey the energy principles. However, energy was not conserved because it lost energy due to air friction, and as I mentioned before, the spring constant deteriorates as the spring is lengthened and shortened. And our period of oscillation. So as you can see here, the difference in each peak is about 1.7 seconds, and that is to be expected since it's the same spring. We should have a similar oscillation regardless of which direction it's in. So x and y, you can see that that is still about 1.7 seconds between each valley or peak.